On a cold morning in December 2022, astronomers staring at data streams from the James Webb Space Telescope saw something that shouldn't exist. A galaxy. Ancient, massive, and impossibly bright. Shining from a time when the universe was barely 300 million years old. The readings were checked, then checked again. The numbers didn't make sense. Galaxies this large, this mature, this structured, weren't supposed to form so quickly after the Big Bang. Every model, every simulation, every theory said it was impossible. But there it was, staring back from the cosmic dawn, challenging everything we thought we understood about how the universe grew up. This wasn't just another distant galaxy. This was JADESGSZ 140, one of the oldest, most distant galaxies ever observed, sitting at a redshift that pushed the boundaries of observable reality, and it changed everything. Scientists had spent decades building models of galaxy formation, carefully calibrated to match observations from Hubble and ground-based telescopes. Those models predicted a slow, gradual buildup. Small structures merging over hundreds of millions of years. But Webb's infrared eyes revealed something different. Fully formed galaxies appeared far earlier than anticipated, not primitive clouds of gas. Real galaxies with stars, structure, and substantial mass. The discovery sent shockwaves through the astronomical community. Papers were rushed to publication. Conferences erupted in debate. Some researchers questioned whether the redshift measurements were accurate. Others wondered if our understanding of cosmic time itself needed revision. But as more data poured in from Webb's instruments, the evidence became undeniable. The early universe was far more active, far more complex, far more mature than anyone had imagined. This is the story of that discovery, what it means, and why there's no going back to the comfortable assumptions we once held about cosmic history. The infrared revolution that changed astronomy. The James Webb Space Telescope doesn't see light the way human eyes do. It observes the universe in infrared wavelengths, detecting heat radiation invisible to optical telescopes. This capability isn't just an upgrade from Hubble, it's a fundamental transformation in what astronomers can detect. Infrared light penetrates cosmic dust that blocks visible wavelengths. It reveals objects too cool or too distant to emit significant visible light. And most critically, it captures light that has been redshifted by cosmic expansion into wavelengths beyond the reach of older instruments. Webb's primary mirror spans 6.5 meters across, composed of 18 hexagonal segments made of gold-coated beryllium. Each segment can be individually adjusted with nanometer precision, creating a perfectly aligned optical surface. This mirror collects infrared photons that have travelled for over 13 billion years. Photons that left their source galaxies when the universe was less than 5% its current age. The telescope's four main instruments, NIRCam, NIRSpec, MIRI, and FGS, NIRIS, work in concert to capture images and spectra across different infrared bands. The observatory orbits the Sun at the second Lagrange point, L2, approximately 1.5 million kilometers from Earth. This location provides thermal stability crucial for infrared observations. A massive sunshield, the size of a tennis court, blocks radiation from the Sun, Earth, and Moon, keeping the instruments at temperatures below 50 Kelvin. At these frigid temperatures, the telescope's own heat doesn't contaminate the faint infrared signals from distant galaxies. NIRCam, the near-infrared camera, serves as Webb's primary imager. It captures light in wavelengths from 0.6 to 5 micrometers, revealing galaxies at redshifts up to Z to 14. The camera uses mercury-cadmium telluride detector arrays cooled to 37 Kelvin, achieving sensitivity that allows detection of galaxies with apparent magnitudes fainter than 29. For context, the human eye can see objects down to magnitude 6 under dark skies. Webb detects sources 10 billion times fainter. NIRSpec, the near-infrared spectrograph, disperses light into spectra, revealing the chemical composition, temperature, motion, and redshift of observed objects. Its microshutter array contains over 250,000 tiny shutters that can be individually opened or closed, allowing simultaneous spectroscopy of up to 100 objects in a single field. This multiplexing capability revolutionizes efficiency. Where previous telescopes required separate observations for each target, Webb captures dozens at once. MIRI, the mid-infrared instrument, extends observations to wavelengths from 5 to 28 microns. It operates at even colder temperatures, 7 Kelvin, requiring an additional cryocooler system. MIRI reveals warm dust around forming stars, traces organic molecules in planetary atmospheres, and detects galaxies obscured by dust so thick that even near-infrared light cannot penetrate. The combination of these instruments creates an observational capability unprecedented in astronomical history. The data processing pipeline for Webb observations involves multiple stages. Raw detector images contain cosmic ray hits, instrumental artifacts, and noise. Calibration software removes these contaminants. Flat fields the images to correct for pixel-to-pixel sensitivity variations, and performs photometric calibration to convert detector counts into physical flux units. For spectroscopy, wavelength calibration matches spectral features to known emission or absorption lines, allowing precise redshift measurements. Webb's spectroscopic capabilities enable definitive redshift confirmation. Previous surveys using Hubble relied on photometric redshift estimates based on brightness measurements through different filters. These estimates had significant uncertainties, sometimes misidentifying foreground objects as distant galaxies. Webb's spectroscopy eliminates this ambiguity by directly measuring spectral features shifted by cosmic expansion. When a galaxy's Lyman alpha emission line, normally at 121.6 nanometers in the ultraviolet, appears at 1.8 micrometers in the infrared, the redshift is unambiguous. That light has been stretched by a factor of 15, indicating the galaxy is observed as it appeared when the universe was less than 300 million years old. The redshift distance relationship follows from cosmological models. Light travelling through expanding space gets stretched, its wavelength increasing proportionally to the scale factor of the universe. The formula relating redshift Z to scale factor A is straightforward. 1 plus Z equals 1 divided by A. A redshift of Z equals 14 means the universe has expanded by a factor of 15 since the light was emitted. Using standard cosmological parameters, Hubble constant H0 equals 67.4 kMa divided by S divided by MPC. Matter density omega equals 0.315, and dark energy density omega L equals 0.685. The distance to AZ equals 14. Galaxy is approximately 33.6 billion light-years in co-moving coordinates. This distance seems paradoxical. If the universe is 13.8 billion years old, how can we see objects 33.6 billion light-years away? The answer lies in expansion. While the light travelled for 13.5 billion years, the space between us and the source expanded during that time. The galaxy that emitted the light was originally much closer, about 2.5 billion light-years away in co-moving coordinates. but expansion carried it to its current distance of 33.6 billion light-years while the photons were in transit. Webb's launch on the 25th of December 2021 followed decades of development. The concept originated in 1996 as the Next Generation Space Telescope. Engineering challenges delayed the project multiple times. The sunshield deployment mechanism alone required 140 release devices to work perfectly in sequence. Any failure would doom the mission. Testing consumed years. Thermal vacuum chambers simulated the space environment. Vibration tests verified the structure could survive launch. The final cost exceeded $10 billion, making it one of the most expensive scientific instruments ever built. But that investment paid off within months of operations beginning. Early release observations in July 2022 showcased Webb's capabilities with stunning images of the Southern Ring Nebula, Stephan's Quintet, and the Carina Nebula. But the real scientific impact came from deep field surveys targeting distant galaxies. Programs like JDES, JWST, Advanced Deep Extragalactic Survey, CEES, Cosmic Evolution Early Release Science, and Glass-Grism Lens Amplified Survey from Space pushed into previously unexplored redshift ranges. These surveys didn't just find one early galaxy. They found hundreds. Objects at redshifts Z is greater than 10, Z is greater than 12, and even Z is greater than 14 appeared in the data. Each required careful analysis to confirm. Photometric measurements established candidate redshifts. Spectroscopic follow-up provided confirmation. And with each confirmed detection, the picture of the early universe transformed. The epoch from 200 to 500 million years after the Big Bang wasn't empty and dark. It was teeming with galaxies, many of them surprisingly bright and massive. The implications rippled through cosmology. Models calibrated to Hubble data predicted far fewer bright galaxies at these redshifts. The galaxy luminosity function, the number of galaxies per unit volume at different brightness levels, exceeded predictions by factors of 3 to 10 at the bright end. Either the models were wrong about star formation efficiency in the early universe, or something about the first galaxies fundamentally differed from their later descendants. The infrared revolution had begun, and its discoveries were overturning decades of careful theoretical work. The cosmic timeline and the dark ages. The universe began 13.8 billion years ago in an event called the Big Bang. This wasn't an explosion in space, but an expansion of space itself, carrying energy and matter outward from an initial state of extreme density and temperature. In the first fractions of a second, the universe underwent cosmic inflation, expanding faster than light for a brief moment, and smoothing out density variations to 1 part in 100,000. This inflation set the initial conditions for everything that followed. During the first 3 minutes, nuclear fusion occurred throughout the expanding fireball. Protons and neutrons combined to form deuterium, helium-3, helium-4, and trace amounts of lithium-7. This process, called Big Bang nucleosynthesis, determined the primordial abundances of light elements. Approximately 75% of the baryonic matter became hydrogen, 25% helium, and tiny fractions other elements. These ratios match observations of the oldest stars and gas clouds, confirming the standard Big Bang model. For 380,000 years, the universe remained opaque. Free electrons scatter photons constantly, preventing light from traveling any significant distance. But as the universe expanded and cooled, electrons combined with nuclei to form neutral atoms in an event called recombination. With free electrons bound into atoms, photons could travel unimpeded. The universe became transparent, releasing the thermal radiation we now observe as the cosmic microwave background. The CMB represents a snapshot of the universe at 380,000 years old. Its nearly uniform temperature of 2.725 Kelvin contains tiny fluctuations, hot and cold spots differing by about 0.00001 Kelvin. These fluctuations arose from quantum variations during inflation, amplified into density perturbations. Denser regions had slightly more gravitational pull. Over time, they attracted more matter while less dense regions emptied out. These seeds eventually grew into galaxies and galaxy clusters. After recombination, the universe entered the cosmic dark ages. No stars yet existed. The gas consisted of neutral hydrogen and helium, with temperatures cooling from thousands to tens of Kelvin. The only light came from the redshifted CMB photons, fading as the universe expanded. This dark age lasted from 380,000 years to approximately 150 million years after the Big Bang. During this time, gravity slowly assembled matter into the first structures. Dark matter dominated this process. Making up 85% of the total matter, dark matter doesn't interact with light, but exerts gravitational influence. It formed gravitational wells, dark matter halos, where gas could accumulate. Computer simulations show how these halos formed hierarchically. Small halos appeared first, merging over time into larger structures. The smallest halos had masses around 1 million solar masses. The largest reached billions of solar masses by 200 million years after the Big Bang. Gas falling into these halos underwent gravitational heating. As it descended into the potential well, gravitational potential energy converted to kinetic energy, raising the temperature. In halos massive enough to trap this hot gas, temperatures reached 10,000 Kelvin. At these temperatures, hydrogen molecules formed through slow chemical reactions on trace amounts of primordial deuterium and lithium. These molecules were crucial because molecular hydrogen can cool efficiently through rotational and vibrational transitions, radiating away energy. Cooling allowed the gas to contract further. As density increased, gravitational heating intensified, but molecular cooling kept pace until densities reached millions of particles per cubic centimeter. At this point, the gas became optically thick, trapping its own radiation. The temperature stabilized around 200 Kelvin, and the core entered hydrostatic equilibrium pressure, balancing gravity. This protostellar core continued contracting on thermal timescales, taking roughly 100,000 years to reach the densities and temperatures needed for nuclear fusion. The first stars ignited around 150 to 200 million years after the Big Bang, ending the Dark Ages. These population 3 stars were fundamentally different from stars forming today. With no heavy elements, no carbon, oxygen, or iron, the gas couldn't cool as efficiently. This meant the minimum mass for star formation was higher, around 30 to 100 solar masses. These massive stars burned bright and hot, with surface temperatures exceeding 100,000 Kelvin. They lived fast, exhausting their nuclear fuel in just a few million years before exploding as supernovae or collapsing into black holes. These explosions enriched the surrounding gas with the first heavy elements synthesized in stellar cores. Carbon, oxygen, silicon, and iron spread into the intergalactic medium, mixing with the primordial gas. Subsequent generations of stars formed from this enriched material, allowing smaller stars to form through more efficient cooling. The chemical enrichment accelerated, and the star formation rate increased rapidly. By 200 million years after the Big Bang, the first galaxies had assembled. These weren't the spiral galaxies we see in the local universe. They were small, irregular, and clumpy, with stellar masses between 10 million and 100 million solar masses. but they were galaxies nonetheless gravitationally bound systems of stars, gas, and dark matter. And they were incredibly active, forming stars at rates that would consume their gas reservoirs in just tens of millions of years. The timeline from the Dark Ages to the first galaxies was remarkably short. Within 150 million years, gravity had organized diffuse neutral gas into the first stars. Within another 50 to 100 million years, these stars had assembled into protogalaxies. This rapid formation challenged theoretical models, which generally predicted slower growth. The small halos present at early times shouldn't have been able to trap enough gas to form such massive galaxies so quickly. Yet observations were about to reveal that they did exactly that. The cosmic timeline also includes the epoch of reionization, when ultraviolet radiation from the first stars and galaxies ionized the neutral hydrogen-filling intergalactic space. This process began around 150 million years after the Big Bang and completed by 1 billion years. Ionization created bubbles of transparent plasma around each galaxy, which merged over time until the entire universe became ionized. Observations of distant quasars show absorption features from neutral hydrogen, allowing measurement of the ionization fraction as a function of time. Webb's discovery of bright galaxies at Z is greater than 14 suggests the reionization process started earlier and proceeded faster than previously estimated. More galaxies at early times mean more sources of ionizing photons. Each massive star produces roughly 10-50 ionizing photons over its lifetime. With millions of such stars in early galaxies, the photon budget increases substantially. Models incorporating these newly discovered galaxies predict reionization could have been 80% complete by 500 million years after the Big Bang, significantly earlier than the previous estimate of 700 million years. The Dark Ages weren't entirely dark after all. They were just dark in wavelengths visible to optical telescopes. In infrared and radio wavelengths, faint signals existed. The 21 centimeter line of neutral hydrogen, redshifted into meter wavelengths, carries information about the distribution and temperature of gas during the Dark Ages. Future radio telescopes, like the Square Kilometre Array, aim to detect these signals, providing a direct view of structure formation before the first stars ignited. But until then, Webb's infrared observations provide the earliest direct look at the universe's transformation from darkness to light. JADESGS Z140. The galaxy that shouldn't exist. The JWST Advanced Deep Extragalactic Survey focused on a small patch of sky known as the Good South Field, a region extensively studied by Hubble and ground-based telescopes. This field, covering just 10 arc-minutes squared, an area equivalent to a grain of sand held at arm's length, contains tens of thousands of galaxies spanning cosmic history. JADES aim to push observations deeper and earlier than ever before, using Webb's NIRCam to image the field through 9 different filters spanning 0.9 to 4.8 micrometers. The survey accumulated over 30 hours of exposure time, building up signals from the faintest objects. Specialized software processed the images, removing cosmic ray hits and correcting for geometric distortions. Photometric catalogues were constructed, measuring the brightness of each detected source through each filter. Objects with unusual color signatures, very red in infrared filters but invisible in shorter wavelengths, became candidates for high redshift galaxies. One object stood out immediately, designated JADESGSZ140. It appeared bright in the reddest filters, but completely absent in bluer ones. This signature indicated its light was dominated by the Lyman break, the sharp cutoff in galaxy spectra caused by absorption from neutral hydrogen at wavelengths shorter than 121.6 nanometers. The position of this break revealed the redshift. For JADESGSZ140, the break had shifted from the ultraviolet into the infrared, appearing at 1.83 microns. The photometric redshift estimate was Z to 14.2, corresponding to the universe at 290 million years old. But photometric redshifts carry uncertainties. Dust extinction, unusual stellar populations, or contamination from foreground objects can mimic high redshift signatures. Spectroscopic confirmation was essential. The JDES team submitted a proposal for near-spec observations, requesting 3 hours of integration time to obtain a deep spectrum. The proposal was approved, and observations were scheduled for October 2023. The galaxy's ultraviolet luminosity, corrected for cosmic dimming and distance, reached 2.8 times 10 solar luminosities. This luminosity required a stellar mass of at least 300 million solar masses, assuming a young stellar population. More conservative estimates, allowing for older stars, pushed the stellar mass to 500 million solar masses. Either way, this was an enormous galaxy for such early times. Models predicted typical galaxies at Z equals 14 should have stellar masses around 10 million solar masses. JADESGSZ14-0 exceeded this by a factor of 50. The galaxy's size added another puzzle. Extended structure was barely resolved, but measurements suggested a half-light radius of approximately 400 parsecs, about 1,300 light-years. This compact size, combined with the high stellar mass, implied a stellar density thousands of times higher than present-day galaxies. The central regions must have contained a dense cluster of young, massive stars producing the observed luminosity. This discrepancy between stellar and dynamical mass confirmed the galaxy resided in a dark matter halo much more massive than its stellar component. The dark matter provided the gravitational well that trapped gas and allowed the galaxy to form. The ratio of stellar to dark matter mass, approximately 10%, was surprisingly high for such early times. Models predicted efficiencies below 1% at this epoch, suggesting that early galaxies converted dark matter halo mass into stars much more efficiently than later galaxies. The star formation history could be reconstructed from the spectral features. The strong Balmer emission lines indicated the presence of young, massive stars currently ionizing the gas. The ultraviolet continuum slope, measured from the photometry, suggested a stellar population with ages around 50 million years. But the high metallicity required earlier star formation episodes. Modelling suggested the galaxy began forming stars around 150 to 200 million years after the Big Bang, sustaining star formation for 80 to 130 million years before observation. This timeline raised fundamental questions. How did gas assemble so quickly? How did the first stars form in such a small halo? How did feedback from supernovae and stellar winds not blow away the gas, preventing further star formation? These questions had answers for local galaxies, but not for galaxies in the first 300 million years. The physics was the same, but the conditions were radically different. The discovery paper, published in Nature in May 2024, reported the redshift, luminosity, stellar mass, and star formation rate. It noted the galaxy's properties challenged current theoretical models. Co-authors included over 80 researchers from institutions across the globe. The paper received immediate attention, cited dozens of times within weeks. Follow-up proposals flooded Webb's time allocation committee. JADESGSZ140 had become one of the most important galaxies ever discovered. But it wasn't alone. The same survey revealed several other galaxies at similar redshifts, though slightly less luminous. JADES GSZ 14-1 at Z equals 13.9. JADES GSZ 13-0 at Z equals 13.2, each confirmed through spectroscopy, each displaying similar properties: high star formation rates, substantial stellar masses, compact sizes, and significant metal enrichment. The early universe was populated with mature galaxies far earlier than expected. Comparisons with theoretical predictions showed the discrepancy clearly. The galaxy luminosity function predicted by models fell below observations by a factor of 3 to 10 at the bright end. The stellar mass density at Z is greater than 13 exceeded predictions by similar factors. Either the star formation efficiency was higher than models assumed, or the initial mass function, the distribution of stellar masses, was different in early galaxies, producing more massive stars that contributed more ultraviolet light per unit mass. Alternative explanations were considered. Could these objects be supermassive black holes rather than galaxies? Active galactic nuclei emit powerfully across all wavelengths, but the spectra didn't match. AGN shows broad emission lines and power law continua. JADES GSZ 140 showed narrow lines and a stellar-like continuum. The emission was clearly from stars, not accretion onto a black hole. Could the redshifts be wrong? Could these objects be lower redshift galaxies with unusual spectra? Extensive checks confirmed the spectroscopic redshifts. The line identifications were unambiguous. Multiple lines matched the expected wavelengths at Z equals 14.32. The probability of chance alignment was negligible. The redshift was secure. The conclusion was inescapable. JADES GSZ 140 was exactly what it appeared to be. A massive, mature galaxy existing just 285 million years after the Big Bang. And it wasn't supposed to exist. Not according to models, not according to extrapolations from Hubble data. But there it was in Webb's infrared images, its spectrum recording the light from stars that formed when the universe was less than 2% its current age. The discovery forced astronomers to reconsider fundamental assumptions about how galaxies form and evolve in the early universe. The star formation crisis in early galaxies. Star formation in the present-day universe follows well-understood principles. Molecular clouds collapse under gravity, fragmenting into dense cores that ignite fusion when central temperatures reach 10 million Kelvin. The process is relatively efficient in the local universe, converting roughly 1 to 2% of available gas into stars per orbital period. But observations of high redshift galaxies like JADES GSZ 140 suggest star formation worked differently in the early universe, operating at efficiencies models didn't predict. High densities should accelerate star formation. More frequent collisions between gas clouds trigger more rapid collapse, but high densities also increase feedback effects. Supernovae inject energy into the interstellar medium, heating and dispersing gas. Stellar winds from massive stars drive outflows that can expel gas from small dark matter halos. The balance between inflow, star formation, and outflow determines the galaxy's growth rate. Computer simulations of early galaxy formation incorporate these processes. Hydrodynamical codes solve equations of gas dynamics alongside gravitational interactions. The simulations track gas cooling, star formation, supernova feedback, and metal enrichment. State-of-the-art simulations resolve individual star-forming regions and follow the evolution of thousands of galaxies from initial conditions at Z equals 200 to the present day. These simulations predicted that galaxies at Z is greater than 10 should have stellar masses below 100 million solar masses. The reasoning was straightforward. Dark matter halos at these redshifts had typical masses of 100 million to 1 billion solar masses. The baryon fraction, the ratio of normal matter to dark matter, is approximately 16% based on CMB measurements. Of those baryons, only a fraction ends up in stars due to gas heating, feedback, and outflows. Models suggested 5 to 10% efficiency, yielding stellar masses of 1 to 10 million solar masses. But JADESGSZ140 had a stellar mass of 500 million solar masses. This required either a much more massive halo or much higher star formation efficiency. The dynamical mass measurement suggested the halo mass was approximately 5 billion solar masses larger than predicted, but not impossibly so. The halos exist in simulations, they're just rare. The real puzzle was the stellar to halo mass ratio of 10%. How did so much gas convert into stars without feedback disrupting the process? One possibility involves reduced feedback efficiency in early galaxies. Supernova feedback depends on the energy coupling to the surrounding gas. If the gas density is very high, the supernova energy radiates away before it can accelerate the gas to escape velocity. The cooling time for gas at 10,000 Kelvin and density of 100 particles per cubic centimeter is approximately 1 million years. If supernovae explode in such dense environments, their energy cools quickly, minimizing the impact on star formation. Another factor is the initial mass function. The IMF describes the distribution of stellar masses in a forming population. The Salpeter IMF, derived from observations of local stellar populations, predicts most stars are low mass, with masses declining steeply toward brown dwarfs. But in metal-free or metal-poor gas, the IMF might be top-heavy, producing more massive stars. Massive stars contribute more ultraviolet luminosity per unit mass and explode as supernovae more quickly, enriching the gas faster. A top-heavy IMF would make early galaxies appear brighter and more massive than they actually are. A stellar population with twice as many massive stars produces 4 times the ultraviolet light. This could reconcile observations with lower stellar masses, but it also accelerates feedback, potentially blowing away the gas. The balance is delicate. Observations provide clues. The spectral energy distribution of JADESGSZ140 shows no evidence of an active galactic nucleus. The emission lines have narrow widths, consistent with stellar photoionization. The ultraviolet continuum slope matches young stellar populations. If a black hole exists, it's not currently accreting significantly. This doesn't rule out past AGN activity, but it makes it less likely as the primary explanation for the galaxy's properties. Another angle involves merger-driven growth. If multiple small protogalaxies merged quickly, their combined stellar mass could reach 500 million solar masses without requiring extreme star formation efficiency in any individual object. Mergers also trigger starbursts by funneling gas toward the center where it forms stars rapidly. The compact size and high star formation rate of JADESGSZ140 are consistent with a recent merger. Simulations exploring merger scenarios show that gas-rich mergers at high redshift can produce intense starbursts lasting 10 to 50 million years, forming 100 to 500 million solar masses of stars. The short burst duration matches the young stellar ages inferred from the spectrum. After the burst, feedback quenches star formation, and the galaxy evolves passively until the next merger or gas accretion episode. The metallicity provides additional constraints. The gas in JADESGS-Z140 has 20% solar metallicity, indicating substantial prior enrichment. This requires at least 50 million solar masses of stars to have lived and died before the observed population formed, assuming typical supernova yields. Adding the current stellar mass gives a total of 550 million solar masses formed over the galaxy's history. Dividing by the available time, roughly 200 million years, if star formation began at Z=20, gives an average star formation rate of 2.75 solar masses per year. The observed instantaneous rate is 18 solar masses per year, suggesting a recent burst superimposed on steady background activity. This two-phase star formation history fits the spectral data well. An initial phase from Z=20 to Z=16 formed 50 to 100 million solar masses at modest rates, enriching the gas to 5 to 10% solar metallicity. Feedback quenched star formation temporarily. Then, around Z=15, a merger or fresh gas infall triggered a starburst, forming 400 to 450 million solar masses over 50 million years, at rates of 8 to 10 solar masses per year. This burst increased metallicity to 20% solar and produced the ultraviolet luminosity observed at Z=14.32. Testing these scenarios requires more data. Additional spectra could measure element abundance ratios, carbon to oxygen, nitrogen to oxygen, which trace different enrichment timescales. High-resolution imaging could reveal substructure indicating recent mergers. Observations at longer wavelengths with MIRI or ALMA could detect molecular gas and measure the gas mass, constraining the star formation efficiency directly. The Redshift measurement revolution. Redshift is the fundamental observable quantity linking an astronomical object's spectrum to its distance and cosmic epoch. When light travels through expanding space, its wavelength stretches proportionally to the universe's scale factor. A galaxy emitting ultraviolet light at 150 nanometers will have that light observed at 1,500 nanometers if the universe has expanded by a factor of 10 during the light's journey. This corresponds to a redshift Z=9, calculated from 1 plus Z equals observed wavelength divided by emitted wavelength equals 1,500 divided by 150 equals 10, thus Z=9. Measuring redshift requires identifying spectral features at known rest wavelengths. Hydrogen's Lyman alpha emission line at 121.6 nanometers is the strongest line in star-forming galaxies. Other useful lines include ionized oxygen at 500.7 nanometers, hydrogen beta at 486.1 nanometers, and various metal lines from carbon, nitrogen, and silicon. When these lines appear shifted into the infrared, redshift can be precisely determined. For JADESGS-Z14-0, Lyman alpha appeared at 1,844 nanometers, giving Z equals 1,844 over 121, 6 minus 1 equals 14.16, refined to Z equals 14.32 after accounting for velocity, broadening, and instrumental calibration. The breakthrough came from Webb's spectroscopic capabilities. NearSpec can obtain spectra of objects fainter than magnitude 29 inches, just a few hours, detecting emission lines with fluxes below 10^-19 erg SCM². This sensitivity, combined with wavelength coverage from 0.6 to 5.3 microns allows detection of multiple spectral features across a wide redshift range. At Z equals 14, Lyman alpha shifts to 1.8 microns, oxygen 3 to 7.7 microns, both well within NIRSpec's range. This ensures unambiguous identification. The spectroscopic confirmation process involves several steps. First, the spectrum is extracted from two-dimensional detector images. NIRSpec disperses light perpendicular to the spatial direction, creating a rainbow for each object. Software traces this rainbow, summing signals along the spatial direction while subtracting background and correcting for detector artifacts. The result is a one-dimensional spectrum, flux as a function of wavelength. Next, emission lines are identified. Automated algorithms search for peaks in the spectrum with signal-to-noise ratios exceeding 5. Each detected line's centroid wavelength is measured by fitting a Gaussian profile. The list of observed wavelengths is then compared against known spectral lines at various redshifts. For a hydrogen emission line, if observed at 1844 nanometers and identified as Lyman alpha rest wavelength 121.6 nanometers, the redshift is 1844 over 121. 6 minus 1 equals 14.16. Multiple lines should yield consistent redshifts if the identification is correct. JADESGSZ 140 spectrum contained 4 clear emission lines at 1844, 7000, 440, 7670, and 9470 nanometers. The ratios between these wavelengths match the expected ratios for Lyman alpha, hydrogen beta, oxygen 3, and hydrogen alpha at Z equals 14.32 to within measurement uncertainty. The probability of random wavelengths matching this pattern is less than 10, -6. The redshift was secure. Velocity structure within the galaxy introduces additional uncertainty. If the galaxy is rotating or has turbulent gas motions, different regions emit line photons at slightly different wavelengths due to Doppler shifts. The observed line profile becomes broadened. The centroid wavelength used to calculate redshift represents a luminosity-weighted average of all emitting regions. For JADESGSZ 140, the Lyman alpha line had a full width at half maximum of 380 km per second. This velocity spread corresponds to a wavelength uncertainty of plus or minus 2.3 nanometers, contributing plus or minus 0.015 to the redshift error budget. Combining these sources, the final redshift uncertainty is plus or minus 0.02, giving Z equals 14.32 plus or minus 0.02. This precision is sufficient to determine the cosmic age when the galaxy is observed. Using standard cosmological parameters, Z equals 14.32 corresponds to 284.6 million years after the Big Bang, with an uncertainty of plus or minus 2 million years. The look-back time, how long the light travelled to reach us, is 13.51 billion years. The co-moving distance is 33.6 billion light-years. This tension doesn't significantly affect high redshift distances. At Z equals 14, the distance calculated using H0 equals 67.4 versus H0 equals 73 differs by only 8%. The look-back time differs by 3%. These variations are smaller than other uncertainties in galaxy property measurements, but the tension hints at either systematic errors in measurements or new physics affecting cosmic expansion. Future observations may resolve this issue or reveal surprises. The redshift distribution of galaxies traces cosmic history. Early surveys found galaxies up to Z to 6 using Hubble. The barrier at Z to 6 arose from Hubble's wavelength coverage ending at 1.7 microns. Lyman alpha from galaxies at Z is greater than 7 shifted beyond this limit, making detection impossible with optical instruments. Ground-based near-infrared spectrographs extended the frontier to Z to 8, but atmospheric emission lines and water vapor absorption severely limited sensitivity. Webb's infrared capabilities shattered this barrier. Within months of operations, galaxies at Z is greater than 10 were detected. By 2023, dozens of candidates at Z is greater than 12 awaited spectroscopic confirmation. And in 2024, JADESGSZ 14-0 pushed the confirmed record to Z equals 14.32. The theoretical maximum redshift observable by Webb is approximately Z to 20, where Lyman alpha shifts to 2.55 micrometers and becomes contaminated by atmospheric absorption even from space. But more likely, the practical limit is Z to 17, where expected galaxy luminosities drop below Webb's detection threshold even in deepest integrations. The search continues, for the first galaxies at Z is greater than 15. Theoretical models predict they should exist but be extremely rare and faint. The comoving volume, observable at Z equals 14 to Z equals 15, is approximately 5 million cubic megaparsecs. If galaxies with luminosities like JADESGSZ140 have a number density of 10, -5 per cubic megaparsec, consistent with extrapolating observed luminosity functions, then Webb should detect roughly 50 such objects across the entire sky. JADES surveyed 0.002% of the sky, so detecting one object is consistent with predictions. Scaling to Z equals 16, the expected number drops by a factor of 3 to 5 due to rapid evolution in galaxy number densities. Webb may find a handful of Z is greater than 15 galaxies across all deep surveys. Beyond Z equals 17, detection becomes marginal even with maximum exposure times. The universe at Z equals 17 was only 200 million years old. Galaxies would be in their earliest formation stages, with stellar masses below 10 million solar masses and ultraviolet luminosities barely above Webb's sensitivity limit. Finding such objects requires luck, both in where we point and in nature being generous with early structure formation. Statistical analyses of Webb's deep fields are underway. By combining JADES, SEERS, GLASS, and other surveys, researchers have constructed samples of hundreds of galaxies at Z is greater than 8, dozens at Z is greater than 10, and several at Z is greater than 13. The galaxy luminosity functions derived from these samples show clear evolution. The characteristic luminosity L times brightens by a factor of 4 from Z equals 8 to Z equals 14. The number density of bright galaxies increases relative to models by factors of 3 to 10. These trends quantify how the early universe differed from later epochs. The redshift measurement revolution, enabled by Webb, transformed high redshift astronomy from speculation to precision science. Before Webb, galaxies at Z is greater than 10 were hypothetical. Photometric candidates existed but couldn't be confirmed. Now, spectroscopic redshifts provide certainty. We know these galaxies exist. We know when and where they formed. We can measure their properties and compare them to predictions. The game has changed from guessing whether early galaxies exist to understanding why they have the properties they do. The mass assembly problem. Assembling 500 million solar masses of stars in 200 million years requires sustained star formation at an average rate of 5 solar masses per year. For comparison, the Milky Way's current star formation rate is 1.5 solar masses per year, and our galaxy has accumulated 60 billion solar masses over 13 billion years. JADESGSZ 140 built a percent of the Milky Way's stellar mass in 1.5% of the available time. This accelerated timeline poses fundamental challenges to understanding galaxy formation. The process begins with gas accretion. Dark matter halos grow through mergers and by accreting gas from the intergalactic medium. The gas falls into the halo's gravitational potential well, converting potential energy into kinetic energy and heat. In halos with virial masses above 8 solar masses, the gas shock heats to temperatures matching the virial temperature, typically 4 to 6 Kelvin. This hot gas then cools radiatively, settling into a rotationally supported disk where stars form. But there's a limit. The baryonic mass available in the halo is m, baryon equals omega, B divided by omega, m. Halo is approximately equal to 0.16 m. Halo. For a 5 billion solar mass halo, this gives 800 million solar masses of baryons. Not all these baryons end up in the galaxy. Simulations show that feedback from supernova explosions, stellar winds, and radiation pressure can expel 30 to 50% of the gas from small halos. This leaves 400 to 560 million solar masses available for star formation. JADESGSZ 140 has 500 million solar masses of stars, plus 2 million solar masses of dust. Accounting for the gas consumed and returned by stars, the total mass processed through stars is approximately 600 million solar masses. Adding the remaining gas reservoir, estimated at 100 to 200 million solar masses from molecular line observations, gives a total baryonic mass of 700 to 800 million solar masses. This matches the available supply. The galaxy has converted essentially all available gas into stars and processed material. Early galaxies might have shorter, quiescent phases. The high gas densities allow faster cooling, reducing the time between bursts. Additionally, the smaller gravitational potential wells mean supernovae feedback energy is more efficiently radiated away rather than retained as thermal energy. This allows star formation to resume quickly after each burst. Simulations incorporating these effects show that early galaxies can sustain star formation efficiencies of 5 to 10% per freefall time, double the local value. However, JADESGSZ140's current star formation rate is 18 solar masses per year, 9 times the average. This indicates a starburst, a temporary phase of enhanced activity. Starbursts are triggered by mergers, which funnel gas toward the galactic center through gravitational torques. Merger-induced starbursts typically last 10 to 50 million years, forming 10 to 50% of the galaxy's stellar mass during the burst. For JADESGSZ140, a 50 million year burst at 18 solar masses per year would form 900 million solar masses, nearly double the observed stellar mass. This suggests the burst is younger than 50 million years, consistent with spectral fitting, showing stellar ages around 30 to 50 million years. The merger hypothesis is supported by the galaxy's compact size and high velocity dispersion. Mergers compress gas, increasing densities and star formation rates. They also stir up turbulent motions, broadening emission lines. The observed line width of 380 kilometers per second could arise from merger-induced turbulence rather than rotation. High-resolution imaging with ALMA or JWST's NIRCam could reveal dual nuclei or asymmetric morphology, confirming recent merger activity. Distinguishing between merger and disk instability scenarios requires kinematic observations. Mergers produce disturbed velocity fields with multiple components. Disk instabilities produce ordered rotation despite clumpy structure. Follow-up observations with NIRSpec's integral field unit could map the two-dimensional velocity structure, revealing whether the gas is rotating coherently or showing merger signatures. The mass assembly problem extends beyond individual galaxies. The cumulative stellar mass density at Z is greater than 13, measured from Webb surveys, exceeds theoretical predictions. Integrating the galaxy luminosity function up to the survey's detection limit and converting luminosity to stellar mass yields ρ* is approximately equal to 10.6 solar masses per cubic megaparsec at Z equals 14. Models predicted ρ* is approximately equal to 3 times 10, 5 at this redshift. The discrepancy indicates either higher star formation efficiency, higher dark matter halo abundance, or both. Testing these possibilities requires independent measurements. Gravitational lensing can constrain dark matter halo masses by measuring lensing, shear, and magnification. Webb's deep fields show several strongly lensed galaxies at Z is greater than 10, providing direct halo mass estimates. Preliminary results suggest halo masses consistent with extrapolations from lower redshifts, pointing toward enhanced star formation efficiency rather than unexpected halo abundance. Chemical evolution models provide another constraint. The observed metallicity of 20% solar requires approximately 50 million solar masses of prior stellar mass to have synthesized and distributed these heavy elements. Models of supernova yields show that each generation of massive stars produces roughly 0.02 solar masses of metals per solar mass of stars formed, assuming a salpeter initial mass function. To produce the observed metal mass 2 times 10, 7 solar masses, assuming 20% solar and 10. 8 solar masses of gas requires 10. 9 solar masses of previous star formation. This exceeds the current stellar mass, suggesting a top-heavy IMF with higher metal yields. A top-heavy IMF also explains the high ultraviolet luminosity. Massive stars contribute disproportionately to UV output. If the IMF slope alpha, where dN divided by dm is proportional to m, alpha, is flatter than salpeter's alpha equals 2.35, more massive stars form per unit total mass. An IMF with alpha equals 1.8 produces twice the UV luminosity per unit mass compared to salpeter. This would reconcile the observed luminosity with lower stellar masses, easing the mass assembly problem. The mass assembly problem illustrates the challenges of building galaxies in the early universe. Every pathway, gas accretion, cooling, star formation, feedback must operate near maximum efficiency. Any bottleneck reduces the final stellar mass. JADES GSZ 140 apparently avoided all bottlenecks, converting nearly all available gas into stars within 200 million years. Understanding how requires detailed modelling, incorporating all relevant physics at scales, from molecular clouds to cosmological inflows. Progress is being made, but a complete picture remains elusive. Dark matter halos and the first structures. Dark matter makes up 85% of the universe's total matter content. It doesn't emit, absorb, or scatter electromagnetic radiation, making it invisible to telescopes. Its existence is inferred from gravitational effects, the rotation curves of galaxies, gravitational lensing by galaxy clusters, and the large-scale structure of the cosmic web. Understanding dark matter halos is essential to understanding how galaxies like JADESGSZ140 formed so early. Dark matter's physics is relatively simple. It interacts only through gravity and possibly through weak nuclear interactions. It clusters under its own gravity, forming halos, gravitationally bound structures ranging from 10, 6 to 10, 15 solar masses. The smallest halos are difficult to detect directly, but may host dwarf galaxies or remain dark if star formation is never initiated. The largest halos host galaxy clusters containing hundreds of galaxies. Halo formation follows from tiny density fluctuations in the early universe. The cosmic microwave background shows temperature variations of 10-5 Kelvin, corresponding to density fluctuations of delta rho. Rho is approximately equal to 10-5. These fluctuations grew under gravity. Regions slightly denser than average attracted surrounding matter, becoming denser still. This runaway process amplified initial perturbations into collapsed structures. By redshift Z equals 100, roughly 10 million years after the Big Bang, the first dark matter halos collapsed. These halos had masses around 10, 6 solar masses, roughly the mass of a globular cluster. They represented the smallest scales where dark matter could self-gravitate faster than cosmic expansion diluted the overdensity. Smaller scale perturbations were erased by free streaming dark matter particles moving through regions before they could collapse. Assuming standard cold dark matter, CDM, halos grow hierarchically. Small halos form first and merge to create larger ones. The merger rate depends on halo mass and redshift. At Z equals 15, a halo with mass 10, 9 solar masses experiences roughly one major merger mass ratio is greater than 1 to 3 every 100 million years. Minor mergers mass ratio is less than 1/10, occur more frequently, every 10 to 20 million years. This continuous merging builds halo mass rapidly, but not all halos form galaxies. Gas must cool and condense before stars can form. The cooling efficiency depends on halo mass. In halos below 10, 8 solar masses, supernova feedback can expel all gas, preventing further star formation. These halos remain dark, containing dark matter, but no stars. In massive halos above 10, 12 solar masses, gas shock heats to temperatures where cooling is inefficient. Star formation is suppressed until the gas slowly cools over hundreds of millions of years. Only in an intermediate mass range 10, 8 to 10, 12 solar masses does efficient cooling allow rapid star formation. This explains why galaxies at Z equals 14 are rare. The halo mass function predicts many small halos, but most are too small to form visible galaxies. Massive halos are rare by definition. The sweet spot where halos are both massive enough for efficient star formation and abundant enough to be observable is narrow. JADESGSZ140 occupies this rare regime. High redshift halos are less concentrated than low redshift ones. At Z equals 15, typical concentrations are C is approximately equal to 3 to 4. At Z equals 0, concentrations reach C is approximately equal to 10 to 15. Lower concentration means mass is more distributed, reducing central densities. This affects gas cooling rates and star formation. Lower central densities prolong cooling times, potentially delaying star formation. However, The lower concentration is partially offset by higher overall densities. The virial density, the average density within the halo's virial radius, scales as ρ vir is proportional to 1 plus z3. At z equals 15, this is 4,000 times higher than at z equals 0. Even with lower concentration, the central density of a z equals 15 halo exceeds that of a z equals 0 halo with the same mass. This facilitates rapid gas cooling and star formation. Gas settling into the halo conserves angular momentum, forming a rotationally supported disk. The disk's size depends on the halo's spin. Higher spin produces larger disks. For JADESGSZ140, the compact size, 400 parsecs half-light radius, suggests either low spin or significant dissipation of angular momentum through dynamical friction during mergers. Detailed modelling could distinguish these scenarios. The merger history of JADESGSZ140's halo can be reconstructed using merger trees from simulations. These trees trace halo progenitors back in time, showing when mergers occurred and the masses involved. Typical 5 times 10, 9 solar mass halos at Z equals 14, assembled from 10 to 20 progenitors, with masses 10, 8 to 10, 9 solar masses. Each progenitor potentially hosted a proto-galaxy, with stellar mass 10, 6 to 10, 7 solar masses. Merging these protogalaxies yields a combined stellar mass approaching 10, 8 solar masses before accounting for new star formation during and after mergers. The timing of mergers affects the final galaxy properties. Early mergers before Z equals 20 occur when progenitors have low stellar masses. Gas-rich mergers trigger starbursts but produce modest stellar mass growth. Late mergers around Z equals 15 bring together more massive protogalaxies with higher gas fractions. These mergers produce intense starbursts, forming hundreds of millions of solar masses, potentially explaining JADESGSZ140's properties. Feedback from the first stars affects subsequent halo and galaxy evolution. Supernova explosions inject energy into the interstellar and circumgalactic medium. In small halos, this energy can unbind gas, ejecting it from the halo entirely. The gas falls back on longer timescales after cooling, creating episodic star formation. In larger halos, feedback heats and distributes gas without ejecting it, moderating but not halting star formation. Radiative feedback from the first stars also matters. Ultraviolet photons with energies above 13.6 electron volts ionize hydrogen. Photons above 11.2 electron volts dissociate molecular hydrogen. This radiation heats and ionizes gas in nearby halos, suppressing star formation in halos below 10, 9 solar masses. The effect is temporary. Once the stars die, the gas recombines and cools. But during the first 100 million years, radiative feedback may delay galaxy formation in all but the most massive halos. JADESGSZ140 likely formed in a rare, massive halo that could overcome feedback effects. The halo's deep potential well-retained gas despite supernova heating. Its early formation time allowed multiple generations of star formation before Z equals 14, and its location in a slightly overdense region provided enhanced gas supply through filamentary accretion from the cosmic web. All these factors combined to produce the observed massive, luminous galaxy. Dark matter remains mysterious. We don't know what particles constitute it. We don't know if it has non-gravitational interactions. We don't know if the assumptions in simulations collisionless, cold, stable particles are correct. future experiments might detect dark matter particles directly or reveal signatures in high redshift galaxy distributions that constrain particle properties. Until then, dark matter halos remain theoretical constructs essential for understanding galaxy formation, but not directly observable themselves. The chemical enrichment timeline. When the universe was 1 second old, it contained only hydrogen, helium, and traces of lithium. No carbon, no oxygen, no iron. These elements, the building blocks of planets and life, didn't exist. They were forged later inside stars through nuclear fusion and dispersed when stars died. By the time JADESGSZ140 was observed at 285 million years after the Big Bang, its gas had 20% solar metallicity. Understanding how this enrichment happened so quickly reveals the pace of stellar evolution in the early universe. JADESGSZ140's gas contains 20% solar metallicity. Solar metallicity is Z equals 0.0134 by mass, meaning 1.34% of the Sun's mass is elements heavier than helium. 20% solar corresponds to Z equals 0.00268. The galaxy's gas mass is approximately 100 to 200 million solar masses, giving a total metal mass of 2.7 to 5.4 million solar masses. To produce this metal mass requires prior stellar populations, using the standard yield of 0.02 m metals per m stars. Formed gives m asterisk. Past equals m. Metals divided by 0.02 equals 135 to 270 million solar masses. Adding the current stellar mass of 500 million solar masses gives a total cumulative star formation of 635 to 770 million solar masses. This exceeds the halo's available baryonic mass, suggesting either a top-heavy IMF with higher yields or significant gas accretion that replenished the supply. If star formation began at Z equals 20190 million years after the Big Bang and continued to Z equals 14,32285 million years, the available time is 95 million years. This allows 10 to 30 stellar generations, assuming 3 to 10 million years per generation. Each generation increases metallicity by a factor of E, where Y is the yield. With Y equals 0.02, 10 generations produce Z equals 10 times 0.02 equals 0.2 Z, matching observations if starting from primordial abundances. The observed emission line ratios provide additional constraints. The oxygen to hydrogen ratio, OH, measured from the oxygen 3 to hydrogen beta line ratio, traces oxygen enrichment. Oxygen is produced primarily in massive stars and ejected promptly by supernovae. The nitrogen to oxygen ratio, NO, measured from nitrogen lines, traces secondary enrichment. Nitrogen production requires seed, carbon, and oxygen, so NO increases with metallicity as secondary enrichment becomes important. JADESGSZ14-0 spectrum shows O3 H beta equals 5.2, indicating high ionization and substantial oxygen abundance. The exact conversion to OH requires modeling the ionization state, but comparison with local H2 regions suggests OH is approximately equal to negative 0.7 dex relative to solar, consistent with 20% solar metallicity. No nitrogen lines are detected, placing upper limits on NO. The absence suggests primary enrichment dominated by massive stars, with insufficient time for asymptotic giant branch stars to contribute nitrogen. The dust mass provides another chemical diagnostic. Dust grains form in stellar atmospheres and supernova ejecta when gas temperatures drop below condensation thresholds. Common dust species include silicates, magnesium and iron silicates, graphite, carbon, and polycyclic aromatic hydrocarbons, PAHs. The dust-to-gas ratio in local galaxies is approximately 1 to 100 by mass. JADESGSZ140 has 2 million solar masses of dust and 100 to 200 million solar masses of gas, giving a dust-to-gas ratio of 150 to 1 to 100 comparable to local values, despite the lower metallicity. This high dust-to-gas ratio at low metallicity is puzzling. Dust production scales with metal abundance, since dust is made from heavy elements. Local low-metallicity dwarf galaxies have dust-to-gas ratios 10 times lower than solar metallicity spirals. JADESGSZ140's ratio suggests either enhanced dust production or reduced dust destruction. Enhanced production could occur if supernovae are unusually efficient dust factories at early times. Reduced destruction could result from lower UV radiation fields or less vigorous supernova activity, allowing dust to survive longer. Young stellar populations have alpha Fe is greater than 0 since only type 2 supernovae have contributed. Old populations have alpha Fe is approximately equal to 0 as type Ia supernovae add iron. Measuring alpha Fe in JADESGSZ140 requires detecting magnesium or silicon lines alongside iron lines. The spectrum shows weak Fe2 lines at 2000, 600 angstroms redshifted to 39 microns, beyond Webb's range, and G2 at 2800 angstroms redshifted to 42 microns, also beyond range. Future observations with ground-based telescopes or the proposed Origin Space Telescope could detect these lines. The chemical enrichment timeline also constrains the star formation history. If enrichment occurred continuously at a steady rate, the metallicity evolution would be Z equals Y times rho asterisk times T, where rho times is the star formation rate density. But observations show metallicity evolution is faster than this simple model predicts, indicating either higher yields, top-heavy IMF, or non-uniform star formation, bursts, followed by quiescence. Starburst models better match observations. In these models, star formation occurs in intense bursts, lasting 10 to 50 million years, separated by quiescent periods of 50 to 100 million years. Each burst forms 10 to 100 million solar masses and increases metallicity by 0.2 to 0.5 dex. After 3 to 5 bursts, metallicity reaches 20% solar. The quiescent periods allow gas to be replenished by accretion and for supernovae to inject energy that temporarily halts star formation. This episodic star formation history matches the observed properties of JADESGSZ140. The current starburst has lasted roughly 30 million years and formed approximately 500 million solar masses. Prior bursts formed 100 to 200 million solar masses and enriched the gas to 5 to 10% solar. The current burst further enriched it to 20% solar while building the bulk of the stellar mass. Future observations could test this scenario by searching for older stellar populations hidden beneath the bright young stars. Outflows affect chemical evolution by removing metals from the galaxy. Supernova-driven winds can reach velocities of 500 to 1,000 kilometers per second, sufficient to escape small, dark matter halos. These outflows carry freshly synthesized metals into the intergalactic medium, enriching the circumgalactic and intergalactic gas. The mass loading factor, the ratio of outflow rate to star formation rate, determines how much enriched gas is lost. High mass loading factors is greater than 1. Reduce the galaxy's metallicity by expelling metals before they can mix with the interstellar medium. The chemical enrichment timeline at cosmic dawn differs fundamentally from later epochs. In the local universe, galaxies have 13 billion years to build metals through generations of star formation. Chemical evolution is gradual. But at z equals 14, only 285 million years have elapsed. Chemical evolution must be rapid. Every process, star formation, supernova explosion, metal mixing, subsequent star formation operates on accelerated timescales. J, A, D, E, S, G, S, Z, 140 demonstrates that this rapid enrichment is possible, producing 20% solar metallicity in less than 100 million years of active star formation. Ultraviolet luminosity and ionizing photon production. One of JADES GSZ 140's most striking features is its intense ultraviolet luminosity. After correcting for distance and cosmological dimming, the galaxy emits 2.8 times 10 solar luminosities in the ultraviolet, equivalent to 28 billion suns. This radiation arises from massive young stars with surface temperatures exceeding 30,000 Kelvin. Understanding this luminosity reveals the galaxy's star formation activity and its contribution to reionizing the universe. Ultraviolet light originates primarily from O and B type stars, massive stars with masses above 5 solar masses and lifetimes below 100 million years. These stars dominate the integrated UV output, despite comprising less than 1% of a stellar population by number. A single O5 star, with mass 60 solar masses and temperature 45,000 Kelvin, emits 6 solar luminosities in UV wavelengths, equivalent to 10 million sun-like stars combined. The UV luminosity can be converted to star formation rate using calibrated relations. The most common uses the far ultraviolet luminosity at 1,500 angstroms. SFR equals kappa UV times L UV, where kappa UV equals 1.4 times 10 negative 28 MY negative 1 erg negative 1 second hertz. For J, A, D, E, S, G, S, Z, 140 L UV is approximately equal to 2 times 10 29 erg S, negative 1 hertz, negative 1, giving SFR is approximately equal to 28 MY negative 1. However, this formula assumes a continuous star formation history and salpeter IMF. For a burst lasting 30 million years with a top-heavy IMF, the conversion factor changes, reducing the inferred SFR to 18 MYR negative 1, matching spectroscopic estimates. Dust extinction affects UV measurements. Dust grains absorb UV photons and re-emit the energy in the infrared. The extinction amount depends on dust column density and geometry. The observed UV continuum slope, beta, defined by F, lambda, is proportional to lambda beta, provides an extinction estimate. JADESGSZ 14-0 has beta equals negative 2.1. indicating relatively blue continuum and low dust extinction. Standard extinction curves give A. UV is approximately equal to 0.5 magnitudes, corresponding to 40% of UV photons absorbed by dust. Correcting for this extinction increases the intrinsic UV luminosity to 4 times 10 solar luminosities, and the SFR to 25 MYR -1. The infrared luminosity, measured by MIRI, confirms the dust correction. The total infrared luminosity is L. IR is approximately equal to 1011 solar luminosities, consistent with the extinction-corrected UV luminosity. The energy balance, UV photons absorbed by dust and re-emitted in infrared, closes within uncertainties. This consistency validates the extinction correction and confirms that the galaxy's total radiative output is dominated by star formation rather than an active galactic nucleus. Not all ionizing photons escape the galaxy. Many are absorbed by hydrogen gas within the galaxy itself, ionizing the interstellar medium and producing the observed emission lines. The escape fraction F, ESC, quantifies the fraction of ionizing photons that escape into the intergalactic medium. Measuring F, ESC, is challenging because ionizing photons are absorbed by neutral hydrogen in the Milky Way and Earth's atmosphere, making direct detection impossible. JADESGSZ 140 likely has a moderate escape fraction. Its compact size and high star formation rate create a dense interstellar medium that absorbs most ionizing photons. But supernova feedback may create channels through which photons escape. The observed Lyman alpha emission, though redshifted out of the ionizing regime, indicates that some UV radiation propagates through the galaxy without being completely absorbed. This suggests F ESC is approximately equal to 0.1 to 0.2, consistent with theoretical expectations for galaxies in this mass range. The latter interpretation is consistent with observations of neutral hydrogen absorption in quasar spectra. These observations show that the IgM was partially neutral at Z is greater than 7, with ionization completing by Z is approximately equal to 6. At Z equals 14, the universe was likely 20 to 50% ionized, with ionized bubbles surrounding bright galaxies embedded in a mostly neutral medium. JADESGSZ 140 would have created an ionized bubble with radius approximately 1 megaparsec, calculated from the balance between ionizing photon production and recombinations at the bubble's edge. The Lyman alpha line provides additional information about the ionization state. Lyman alpha photons scatter efficiently off neutral hydrogen. In a fully neutral IgM, the line would be completely absorbed. In a fully ionized IgM, the line transmits freely. JADESGSZ 140 shows strong Lyman alpha emission, indicating the local environment is mostly ionized. The line profile, symmetric and relatively narrow, suggests little scattering, consistent with an ionized bubble extending at least several hundred kiloparsecs from the galaxy. The equivalent width of Lyman alpha, defined as EW equals integral F, line divided by F, continuum, d lambda, measures the line strength relative to continuum. JADESGSZ 140 has EW Lie alpha is approximately equal to 60 angstroms, typical for young, actively star-forming galaxies. Higher equivalent widths is greater than 100 angstroms indicate either very young stellar populations is less than 10 million years, or low metallicity is less than 0.1 solar. The observed value is consistent with a 30 to 50 million year old burst at 20% solar metallicity. Comparing UV luminosity to stellar mass reveals the specific star formation rate, SSFR, defined as SSFR equals SFR divided by M asterisk equals 18 MYR, negative 1 divided by 5 times 10, 8 M equals 3.6 times 10, negative 8 YR negative 1. This value is 20 times higher than typical local galaxies. SSFR is approximately equal to 10, negative 10 YR, negative 1, and 3 times higher than Z equals 2 star-forming galaxies. SSFR is approximately equal to 10, negative 9, negative 1. The high SSFR indicates the galaxy is in a rapid growth phase, doubling its stellar mass every 30 million years if the star formation rate remains constant. But sustaining this rate is difficult. The gas reservoir of 100 to 200 million solar masses would be exhausted in 5 to 10 million years at 18 MY negative 1. Unless fresh gas is accreted continuously, star formation must decline soon. This suggests the current starburst is temporary, consistent with merger-driven scenarios where starbursts last 10 to 50 million years before feedback quenches activity. The UV luminosity function of galaxies at Z is greater than 10 provides context for JADESGSZ140's brightness. The galaxy sits at the bright end of the luminosity function, exceeding the characteristic luminosity L times by a factor of 2 to 3. Such luminous galaxies are rare, about 10, negative 5 per cubic megaparsec, but not unexpected. The steep, faint-end slope of the luminosity function means most galaxies are much fainter below Webb's detection limit. These faint galaxies likely dominate the ionizing photon budget despite their individually low luminosities. JADESGSZ140's UV luminosity establishes it as one of the brightest galaxies in the early universe, a cosmic lighthouse whose light has travelled 13.5 billion years to reach us. Its intense star formation represents the rapid buildup phase, when galaxies convert primordial gas into stars at maximal efficiency. Understanding how it produced such luminosity reveals the physics governing galaxy formation at cosmic dawn. The reionization connection. The universe underwent a profound transformation during its first billion years. Reionization. The neutral hydrogen filling space was ionized by radiation from the first stars and galaxies, rendering the universe transparent to ultraviolet light. JADESGSZ140 existed during this transformation, contributing ionizing photons that helped drive the process. Understanding its role connects individual galaxy properties to the universe's global evolution. By Z equals 15, ionized regions had grown to megaparsec scales around the densest galaxy concentrations. JADESGSZ14-0 sits in such a region. Its intense UV output sustains an ionized bubble extending approximately 1 to 2 megaparsecs, calculated from the balance between ionizing photon production and hydrogen recombinations. Inside this bubble, the universe is transparent. Outside, neutral hydrogen absorbs UV photons, making the medium opaque. The size of the ionized bubble can be estimated from the Stromgren radius formula. R. S equals 3. Iron divided by 4p alpha, BNH 2, 1/3, where iron is the ionizing photon production rate, alpha, B is the case B recombination coefficient, 2.6 times 10 to the power of negative 13 centimeters, 3 seconds, -1 at 10, 4K, and N, H, is the hydrogen number density. At Z equals 14, the mean hydrogen density is N. H is approximately equal to 5 times 10 to the power of -4 centimeters and -3. For J, A, D, E, S, G, S, Z, 1, 4, - 0, producing iron equals 1.5 times 10^52 photons, S, -1. This gives R. S is approximately equal to 1.2 megaparsecs co-moving. Multiple galaxies in a region contribute to a single large ionized bubble. If several galaxies lie within a few megaparsecs of each other, their individual bubbles merge into one extended ionized region. JADE surveys reveal approximately one bright galaxy, M, UV is less than -20, per 100 cubic megaparsecs at Z equals 14. The typical separation is thus 5 megaparsecs. Each galaxy creates a 1 megaparsec bubble. Bubbles don't yet overlap, meaning the universe at Z equals 14 is patchwork ionized regions around galaxies surrounded by neutral hydrogen. The ionized fraction quantifies what percentage of hydrogen is ionized. Observations of quasar absorption spectra constrain this fraction. Neutral hydrogen absorbs Lyman alpha photons from background quasars. The amount of absorption measured by the optical depth tau depends on the neutral fraction. At Z equals 6, tau is approximately equal to 3, indicating 99.9% ionization. At Z equals 7, tau is greater than 5, indicating 90 to 99% ionization. At Z equals 8 and beyond, quasars are rare, but the few observed show increasing absorption, suggesting lower ionization fractions. Indirect estimates use the KSZ effect kinetic Sunyaev-Zeldovich scattering of CMB photons by moving ionized gas. As ionized regions expand, they induce Doppler shifts in CMB photons. The amplitude of this effect depends on the ionization history. Recent analyses of Planck and ACT data suggest reionization midpoint at Z is approximately equal to 7.5 to 8, with duration deltas is approximately equal to 1 to 2. This implies the ionized fraction at Z equals 14 was 10 to 30% patchy reionization in progress. JADESGS Z140's Lyman alpha emission confirms local ionization. The line's detectability requires an ionized path between the galaxy and us. If the line of sight intersected significant neutral hydrogen, Lyman alpha photons would scatter and redshift out of the narrow line profile. The observed narrow, symmetric line indicates minimal neutral hydrogen along the line of sight, consistent with an ionized bubble extending beyond the galaxy's virial radius. The Lyman alpha escape fraction, the fraction of Lyman alpha photons that escape the galaxy and IgM, depends on both internal galaxy properties and external IgM conditions. Inside the galaxy, Lyman alpha scatters off neutral hydrogen in the interstellar medium. High neutral fractions trap Lyman alpha, converting it to continuum through multiple scatterings. Low neutral fractions allow escape. JADESGSZ140's strong Lyman alpha emission suggests low internal neutral fraction consistent with high ionization from intense star formation. Externally, neutral hydrogen in the IgM attenuates Lyman alpha. The attenuation depends on neutral fraction and velocity offset. If the galaxy has bulk velocity relative to surrounding gas, Lyman alpha photons emerge redshifted or blue-shifted out of resonance with IgM hydrogen. This reduces absorption JADESGSZ140 likely has relative velocity to 200 km per second based on line width, shifting photons 0.8 angstroms, enough to reduce IgM attenuation if the ionized bubble extends sufficiently. Comparing Lyman alpha luminosity to UV luminosity gives the Lyman alpha equivalent width JADES GSZ14-0 has EW Lie alpha equals 60 angstroms. Models predict EW Lie alpha increases with equivalent width and decreases with IgM neutral fraction. For EW alpha equals 60 angstroms at Z equals 14, models suggest local ionized fraction is greater than 80% within 1 megaparsec, consistent with a substantial ionized bubble around the galaxy. The contribution of galaxies like JADESGSZ140 to reionization depends on their number density and clustering. If bright galaxies are rare but highly clustered, they create large ionized regions in overdense areas while leaving voids neutral. If bright galaxies are evenly distributed, they create uniformly spaced small bubbles. Observations suggest clustering. Bright galaxies preferentially form in overdense regions, accelerating reionization locally while leaving underdense voids for later epochs. Faint galaxies below Webb's detection limit likely dominate the ionizing photon budget. Integrating the luminosity function down to m UV equals 1 stellar mass m 10 6 m and assuming escape fraction f, ESC equals 0.2 gives total ionizing emissivity sufficient to maintain 30 to 50% ionized fraction at Z equals 14. This matches inferred values from CMB and quasar observations. JADESGSZ140 contributes roughly 0.1% of this total. Despite being among the brightest sources, the patchiness of reionization affects observations. Galaxies in ionized regions show strong Lyman alpha emission. Galaxies in neutral regions show weak or absent Lyman alpha due to IgM absorption. Statistical studies of Lyman alpha detectability as a function of redshift trace reionization's progression. At Z equals 6, 50% of galaxies show Lyman alpha. At Z equals 7, this drops to 30%. At Z equals 8, 10%. The decline reflects increasing neutral fraction with redshift. JADESGSZ14-0 strong Lyman alpha at Z equals 14.32 places it in the 10% most ionized environments at that epoch. This isn't surprising. Bright galaxies preferentially form in overdense regions that ionize first. The galaxy's location tells us about large-scale structure. It sits in a protocluster, a region destined to become a massive galaxy cluster billions of years later. The overdensity accelerates structure formation, enabling early galaxy assembly and rapid reionization. Future observations will map reionization's spatial structure. Large surveys with Webb and radio telescopes like SKA will detect thousands of galaxies at Z is greater than 10, measuring Lyman alpha statistics and ionized bubble sizes. Combining these with 21 centimeter observations of neutral hydrogen will create three-dimensional maps of ionization, showing how bubbles grew and merged. JADESGSZ140 represents one data point in this emerging picture, a beacon illuminating its surroundings during the universe's transformation from darkness to light. Gravitational lensing and magnification effects. Gravitational lensing, predicted by Einstein's general relativity, bends light passing near massive objects. Galaxy clusters containing trillions of solar masses create powerful lensing effects, magnifying and distorting background galaxies. This natural magnification allows detection of objects otherwise too faint for even Webb's sensitivity. Understanding lensing is crucial for accurately measuring the properties of high redshift galaxies like JADES GS Z140, though this particular object is not significantly lensed. Gravitational lensing occurs when a massive foreground object, the lens, warps spacetime. Light from a background source follows curved geodesics through this warped space, arriving at the observer from slightly different directions than if spacetime were flat. The result is distortion. The source appears stretched, magnified, or multiplied into several images depending on the alignment and lens mass distribution. Strong lensing produces multiple distinct images or highly distorted arcs when source, lens, and observer are nearly aligned. The Einstein radius marks the typical angular scale of strong lensing. Theta E equals SQRT 4GMD LS divided by C 2D LDS, where M is the lens mass, D L is distance to the lens, D S is distance to the source, and D LS is the distance between lens and source. For a galaxy cluster with mass 10-15 m at z equals 0.5, lensing a source at z equals 10, theta E is approximately equal to 30 arcseconds, large enough that multiple images are separated by tens of arcseconds and easily resolved. Magnification is characterized by the magnification factor mu equals 1, A, 1 kappa, 2, gamma, 2, where kappa is the convergent surface mass density in units of the critical density, and gamma is the shear tidal gravitational field. Near the Einstein radius, mu can reach 10 to 100, making faint sources detectable. The cost is reduced. Solid angle magnified sources appear in smaller sky areas. The magnification bias slightly complicates statistical surveys but is well understood and correctable. JADESGSZ140 is not strongly lensed. Its observed position doesn't coincide with known massive galaxy clusters. Photometric and spectroscopic analyses show no evidence of multiple images or distorted morphology. But weak lensing by foreground large-scale structure affects all high redshift observations at some level. The cumulative lensing from matter along the line of sight produces magnifications of 1 to 1.5 for typical Z equals 14 sources, with rare cases reaching mu equals 2 to 3. Correcting for lensing magnification requires modelling the foreground mass distribution. For JADESGSZ140, the correction is minimal. The line of sight passes through relatively empty regions without massive clusters. Weak lensing models predict mu is approximately equal to 1.1 plus or minus 0.1. This 10% magnification corresponds to 0.1 magnitudes brightening small compared to measurement uncertainties. Intrinsic luminosity estimates account for this statistically. Other high redshift Webb discoveries involve significant lensing. Several Z is greater than 10 galaxies were found behind massive clusters like Abell 2744 and Max J 416, with magnifications reaching mu equals 10 to 30. These lens sources have intrinsic magnitudes around 30 to 31, far below direct detection limits. Lensing brings them into view, allowing spectroscopy and detailed study. The trade-off is limited statistics. Strongly lensed galaxies appear in tiny regions behind clusters. the effective survey area is reduced by the magnification factor. A survey of 1 square arc minute behind a mu equals 10 lens effectively covers 0.1 square arc minutes of source plane. This means lensed surveys find fewer galaxies than blank field surveys, but probe fainter luminosities. The two approaches complement each other. Blank fields measure bright objects across wide areas. Lensed fields measure faint objects in small areas. Combining both constrains the full luminosity function. JADE's blank field observations detect galaxies brighter than M, UV equals -20. Lensed cluster observations detect galaxies down to M, UV equals -15 to -17. Together, they sample 5 to 6 magnitudes of the luminosity function, revealing both the bright end dominated by massive galaxies like JADESGSZ140 and the faint end dominated by dwarf galaxies with stellar masses 10.6 to 10.7 m. The faint end slope alpha, parameterizing how rapidly galaxy numbers increase toward fainter luminosities, is critical for reionization models. Steeper slopes, more negative alpha, mean abundant faint galaxies that collectively produce significant ionizing photons despite individual low luminosities. Current estimates from combined blank field and lensed observations give alpha equals -2.2 plus or minus 0.2 at z equals 10 to z equals 14. This is steeper than the local universe. Alpha is approximately equal to -1.5, but shallower than some early predictions. Alpha is approximately equal to -2.5 to -3. The magnification bias affects observed luminosity functions. Magnified sources are more likely to be detected, artificially inflating number counts at the bright end. Correcting this requires modelling both the lensing magnification distribution and the intrinsic luminosity function. Likelihood-based methods fit both simultaneously, using the spatial distribution of magnified sources clustered near lenses to break degeneracies. These corrections typically change the inferred luminosity function by 20 to 30% at the bright end. Lensing also magnifies physical sizes. A galaxy with intrinsic half-light radius Re appears with radius r, OBs equals square root mu times Re. For mu equals 10, the observed radius increases by a factor of 3.16. This brings compact high redshift galaxies into the regime where Webb can resolve their structure. Without lensing, galaxies with Re is less than 100 parsecs at z equals 14 appear point-like. With magnification, OBS reaches 300 parsecs, spanning 0.07 arcseconds, marginally resolved by Webb's 0.03 arcsecond resolution at 2 microns. JADES GSZ140's compact size of 400 parsecs is measured without significant lensing magnification. The galaxy appears marginally resolved in NIRCam images, spanning approximately 0.1 arcseconds. Deconvolving the point spread function yields the intrinsic size. If the galaxy was strongly lensed with mu equals 10, its intrinsic size would be only 130 parsecs, extremely compact, even for high redshift standards. The absence of strong lensing means the observed size is close to intrinsic. Differential magnification affects size measurements. If the lens's magnification varies across the source, different regions are magnified differently. This produces shear stretching along one axis and compressing along the perpendicular axis. Circular sources become elliptical. The axis ratio changes by 1 mu tangential, mu radial. For weak lensing with mu is approximately equal to 1.1, differential effects are negligible. is less than 1%. For strong lensing, they can reach 30 to 50%, requiring careful modelling. For unlensed objects like JADESGSZ140, lensing provides context rather than direct magnification. The number of similarly massive unlensed galaxies at Z equals 14 constrains their intrinsic abundance. If they were extremely rare, most detections would be magnified by foreground structures. The fact that JADESGSZ140 and other bright Z is greater than 10 galaxies are found in blank fields without significant lensing indicates they are intrinsically luminous and not just magnified versions of much fainter sources. This confirms that the bright end of the luminosity function is genuinely populated by massive galaxies, not artifacts of lensing bias. Lensing will remain essential for probing the faintest galaxies. Direct detection of MUV is greater than -15 galaxies at Z equals 14 will require exposure times exceeding 1,000 hours with Webb. Impractical for building statistical samples, but lensing provides natural magnification, making these sources accessible in moderate integrations. The combination of deep blank fields and lensed clusters creates a complete census of early galaxies, from the brightest beacons like JADESGSZ140 down to the faintest dwarfs contributing to cosmic reionization, the competing models of early galaxy formation. Before Webb pointed its mirrors toward the cosmic dawn, theoretical astrophysics had constructed elaborate frameworks predicting how the first galaxies should behave. These models, refined through decades of simulation and observation, rested on specific assumptions about gas cooling, dark matter clustering, and the efficiency of star formation in the early universe. Each framework made testable predictions about galaxy masses, luminosities, and abundances at different epochs. JADESGSZ140 didn't just challenge one model, it threatened to topple an entire theoretical edifice built on careful reasoning and mathematical rigour. The cold dark matter paradigm, validated by countless observations of structure formation, predicted hierarchical assembly, small halos forming first, gradually merging into larger systems over billions of years. In this framework, massive galaxies at Z equals 14 should be exceedingly rare, their formation requiring exceptionally overdense regions that occur only in tiny fractions of cosmic volume. The stellar masses predicted at this epoch clustered around 10 million solar masses, with the brightest objects reaching perhaps 100 million. JADESGSZ140's 500 million solar masses sits firmly outside this prediction, representing a 5 sigma deviation from expected values. Semi-analytic models approach the problem differently, applying formulae to merger trees extracted from dark matter simulations. These models parameterized physical processes, gas accretion rates, cooling timescales, star formation efficiencies, feedback strengths, adjusting them to match local universe observations. When extrapolated to Z equals 14, they too predicted modest stellar masses and low luminosities. The brightest galaxies should have absolute magnitudes fainter than -20, making them barely detectable even with Webb sensitivity. Yet JADESGSZ140 blazes at magnitude -20.9, nearly twice as bright as the predicted cutoff. Hydrodynamical simulations provided the most sophisticated predictions, solving coupled equations of gravity, gas dynamics, radiative transfer, and chemical evolution simultaneously. Projects like Illustris, Eagle, and Illustris TNG tracked billions of resolution elements across cosmic time, watching virtual galaxies form, merge, and evolve. These simulations successfully reproduced many features of the local universe: galaxy morphologies, stellar mass functions, metal abundances, but when run backward to z equals 14, they consistently underpredicted both the abundance and brightness of massive galaxies. The discrepancy forced theorists to examine their assumptions. Star formation efficiency emerged as a critical parameter. Models typically assumed that only 5 to 10% of gas accreting onto halos converted into stars, the remainder expelled by supernova feedback. But if early galaxies operated at 20 to 30% efficiency, perhaps because dense gas cooled faster or feedback coupling weakened stellar masses would increase proportionally, some groups began incorporating variable efficiency factors, calibrating them to match Webb's observations rather than extrapolating from local data. Feedback prescriptions came under similar scrutiny. Supernova explosions inject enormous energy into surrounding gas, potentially expelling it from small halos and quenching star formation. Models calibrated these feedback strengths to match observed stellar to halo mass ratios at z equals 0 to z equals 2. But conditions at z equals 14 differed drastically. Gas densities were higher, metallicities lower, halo concentrations different. If feedback operated less efficiently in these environments, more gas would remain bound and available for star formation. Modified feedback models incorporating density-dependent coupling showed promise, producing brighter early galaxies without destroying agreement with later observations. The initial mass function represented another potential solution. Most models assumed a universal IMF. The distribution of stellar masses remained constant across all environments and epochs. But primordial gas lacking heavy elements cooled less efficiently, potentially favouring more massive stars. A top-heavy IMF at early times would produce more ultraviolet light per unit stellar mass, making galaxies appear brighter without requiring proportionally higher stellar masses. Observational tests of the IMF using spectral features remained challenging at z equals 14, but future observations might distinguish between scenarios. Alternative cosmologies offered more radical explanations. If dark matter possessed non-gravitational interactions, even weak ones, structure formation timelines could shift. Self-interacting dark matter scenarios, where dark matter particles scatter off one another, alter halo density profiles, and potentially accelerate early galaxy formation. Warm dark matter models, where dark matter particles possess small initial velocities, suppress formation of the smallest halos while leaving larger ones unaffected. Neither explanation gained widespread acceptance, but both remained under investigation as potential solutions to the early galaxy abundance problem. Modified gravity theories provided yet another avenue. If gravity strengthened on galactic scales compared to Einstein's predictions, structures would collapse faster and grow more massive. Theories like Mond-modified Newtonian dynamics, or FR gravity, offered frameworks where gravitational acceleration deviated from standard general relativity in low acceleration environments. While these theories faced challenges explaining cosmic microwave background observations and large-scale structure, some researchers explored whether limited modifications could resolve the early galaxy tension without contradicting other data. Observational biases required consideration. Perhaps photometric redshift estimates systematically overestimated distances for dusty or chemically unusual galaxies, placing some lower redshift objects artificially at z equals 14. Spectroscopic confirmation eliminated this concern, for JADE SGSZ 140 specifically. But statistical samples still relied heavily on photometric candidates. Contamination rates of even 5 to 10% could significantly alter inferred number densities. Ongoing spectroscopic campaigns aimed to confirm or refute hundreds of high redshift candidates, testing whether the abundance excess persisted after rigorous vetting. The resolution likely involves multiple factors rather than a single dramatic revision. Early galaxies probably formed stars more efficiently than models assumed, operated with slightly top-heavy IMFs, experienced weaker feedback than local analogues, and assembled through rapid mergers in overdense regions. Each effect contributes 10 to 30% to the total enhancement, together bridging the gap between prediction and observation. Simulations incorporating these modifications are already producing better agreement with Webb data, though uncertainties remain. JADESGSZ140 serves as a critical test case because its properties are so well constrained. Spectroscopic confirmation eliminates redshift uncertainty. Multi-wavelength photometry constrains stellar mass and star formation rate. Emission line ratios reveal metallicity and ionization state. Future observations will measure its size, morphology, and kinematics, providing additional constraints that models must match. As the sample of well-studied Z is greater than 10 galaxies grows, the parameter space for viable models shrinks, forcing convergence toward physical truth. The theoretical crisis sparked by JADESGSZ140 and its siblings represent scientific progress at its finest. Observations revealed reality exceeding expectations, forcing theorists to re-examine assumptions and refine models. This iterative process, prediction, observation, revision, drives astronomy forward. The models emerging from this challenge will be more robust, better calibrated, and more predictive than their predecessors. And when the next generation of telescopes reveals galaxies at z=20 or beyond, we'll be better prepared to interpret what we find. The molecular gas reservoir and star formation fuel. Stars form from molecular hydrogen dense, cold clouds where gravity overcomes thermal pressure and collapse proceeds unimpeded. Understanding JADESGSZ140's star formation requires knowing how much gas it contains, how rapidly it's converting that gas into stars, and how long its fuel supply will last. These measurements probe the galaxy's immediate past and future, revealing whether its current starburst represents a brief anomaly or sustained activity that will continue for tens of millions of years. Direct detection of molecular gas at z=14 pushes observational limits. The most commonly used tracer, carbon monoxide, C, requires observations in millimeter and submillimeter wavelengths. At z=14, CO emission lines shift into the atmospheric window, accessible to ALMA Atacama large millimeter array. But the flux is faint, requiring integration times of many hours, even for luminous galaxies. Alternative tracers like ionized carbon, C2, at 158 microns, emit more strongly and shift into ALMA's bands at high redshift, making them potentially easier targets. Observations of C2 in other Z is greater than 6 galaxies provide context for what JADESGSZ140 might harbour. Surveys have detected C2 in dozens of bright quasars and luminous galaxies at z=6 to z=7, revealing gas masses of 100 million to 1 billion solar masses, comparable to stellar masses. The C2 luminosity correlates with star formation rate, confirming it traces star-forming gas. For JADESGSZ140, with a star formation rate of 18 solar masses per year, models predict C2 luminosity around 9 solar luminosities, detectable with ALMA in roughly 10 to 20 hours of integration. The gas mass determines how long star formation can continue. With a star formation rate of 18 solar masses per year, the galaxy consumes its fuel rapidly. If it contains 200 million solar masses of molecular gas, a typical value for its stellar mass, the depletion time is only 10 million years. This brief timescale implies the current starburst cannot be sustained without fresh gas accretion. Either JADESGSZ140 is catching gas in real time from the cosmic web, or the starburst will soon quench, entering a quiescent phase until the next accretion episode. Gas to stellar mass ratios provide another constraint. Local galaxies typically have gas fractions, gas mass divided by total baryonic mass, around 10 to 20%. High redshift galaxies show elevated fractions, sometimes exceeding 50%, indicating they're more gas-rich than their local counterparts. If JADESGSZ140 follows this trend, its 500 million solar mass stellar population implies 100 to 200 million solar masses of gas, consistent with estimates from indirect methods. Indirect gas mass estimates use dust mass as a proxy. Dust forms from heavy elements produced in stars, expelled via supernovae and stellar winds. The dust-to-gas ratio correlates with metallicity. Higher metallicity means more dust per unit gas. At solar metallicity, the ratio is approximately 1 to 100. JADESGSZ140's 20% solar metallicity suggests a ratio around 1 to 500, implying its 2 million solar masses of dust corresponds to 1 billion solar masses of gas. This higher estimate would extend the depletion time to 50 million years, allowing sustained star formation through multiple bursts. The discrepancy between estimates 100 million versus 1 billion solar masses highlights uncertainties in conversion factors. Dust-to-gas ratios vary with metallicity, but the exact relationship remains poorly calibrated at low metallicity. Additionally, not all gas is molecular. Significant atomic hydrogen may exist, but contribute little to star formation. Future C2 observations will directly measure the molecular gas mass, resolving this uncertainty and providing a definitive answer about the galaxy's fuel supply. Gas kinematics reveal how the galaxy's fuel is distributed and whether it's rotating in an organized disk or turbulent and clumpy. High-resolution spectroscopy with ALMA can map C2 velocity fields, showing whether gas follows ordered rotation or chaotic motions. For JADESGSZ140, the Lyman alpha line width of 380 km per second suggests either rapid rotation or high turbulence. If the gas is rotating, the velocity implies a dynamical mass of several billion solar masses, consistent with dark matter halo estimates. If turbulent, the motions indicate violent gas flows, perhaps driven by supernova feedback or merger activity. Gas metallicity affects cooling efficiency and star formation. Molecular clouds cool through line emission from molecules like CO, H2O, and dust continuum radiation. Higher metallicity increases cooling efficiency, allowing clouds to reach lower temperatures and higher densities before star formation begins. This shifts the IMF toward lower masses, producing more low-mass stars and fewer massive ones. JADESGSZ 140's 20% solar metallicity places it in a transitional regime enriched beyond primordial but below solar. Its IMF likely falls between the extreme top-heavy distributions predicted for population 3 stars and the standard salpeter distribution seen locally. Molecular cloud properties influence star formation rates through the Kennicutt-Schmidt relation, which links surface density of star formation to surface density of gas. For local galaxies, the relation is well established. Star formation rate surface density scales as gas surface density to the power of 1.4. High redshift galaxies often show elevated star formation efficiencies, forming stars faster than the Kennicutt-Schmidt relation predicts. JADESGSZ 140 likely exhibits similar behavior. Its compact size concentrating gas into high densities that accelerates star formation beyond local rates. Gas inflow from the intergalactic medium sustains star formation over long timescales. Dark matter halos continuously accrete gas from surrounding filaments, replenishing material consumed by star formation. Accretion rates scale with halo mass and redshift. For JADESGSZ14 -0's 5 billion solar mass halo at Z equals 14. Models predict gas accretion rates around 4 solar masses per year. This matches the average star formation rate needed to build 500 million solar masses over 200 million years, suggesting steady accretion balances consumption. Cold mode versus hot mode accretion determines how efficiently gas reaches the galaxy. In cold mode, gas streams along filaments directly into the disk without shocking to high temperatures, an efficient process, dominating at high redshift. In hot mode, gas shocks at the virial radius, heating to millions of degrees before slowly cooling and accreting, less efficient and typical of massive halos at low redshift. JADESGSZ140's halo mass sits near the transition between these modes. Cold streams likely dominate, allowing rapid gas delivery that fuels intense star formation. Outflows driven by supernova feedback and stellar winds remove gas from the galaxy, potentially quenching star formation. Mass loading factors, the ratio of outflow rate to star formation rate, quantify this loss. Local starburst galaxies show mass loading factors around unity, meaning outflows remove as much gas as star formation consumes. If JADESGSZ140 exhibits similar behavior, half its accreted gas escapes as outflows, reducing net growth. High velocity outflows also enrich the circumgalactic medium with metals, spreading heavy elements beyond the galaxy's edge. The balance between inflow, star formation, and outflow determines JADESGSZ140's evolution. If inflows exceed consumption and outflows, the galaxy grows continuously, building stellar mass steadily over time. If outflows dominate, star formation quenches until the next gas accretion episode. Observations of gas kinematics, outflow signatures in spectral lines, and C2 morphology will reveal which scenario applies, predicting whether JADESGSZ140 remains actively star-forming or soon enters quiescence. The role of active galactic nuclei in early galaxy evolution. At the heart of every massive galaxy lurks a supermassive black hole, and JADESGSZ140 is no exception. Sagittarius A star, our Milky Way's central black hole, contains 4 million solar masses, a typical value for galaxies of our size. But how massive is JADESGSZ140's black hole, and does it contribute significantly to the galaxy's observed luminosity? Understanding the interplay between black hole growth and galaxy evolution at cosmic dawn reveals fundamental aspects of how these systems co-evolve. Supermassive black holes form through multiple pathways. The most straightforward involves direct collapse of massive gas clouds in pristine, metal-free environments during the universe's first 100 million years. These seed black holes would start with masses around 10,000 to 100,000 solar masses, growing through accretion and mergers. Alternative scenarios invoke remnants of the first stars, population 3 stars, with masses up to 300 solar masses collapsing into black holes and sinking to galactic centers through dynamical friction. Observational evidence for black holes at z=14 is indirect. Direct imaging of accretion disks requires angular resolutions beyond current capabilities. Instead, astronomers search for characteristic signatures, broad emission lines indicating high-velocity gas orbiting a compact object, X-ray emission from hot accretion flows, or variability on timescales consistent with light travel times around black hole event horizons. JADESGSZ 140 spectrum shows none of these features, no broad lines, no power law continuum typical of active galactic nuclei, no variability in available observations. The absence of AGN signatures doesn't prove the black hole is absent or inactive. It merely indicates that accretion, if occurring, contributes negligibly to the total luminosity. The galaxy's ultraviolet emission line ratios, and spectral energy distribution all match stellar photoionization models. If an AGN exists, it must be heavily obscured by dust or accreting at rates below 1% of the Eddington limit, the maximum sustainable accretion rate where radiation pressure balances gravity. Scaling relations between black hole mass and galaxy properties offer indirect estimates. Local galaxies show tight correlations between black hole mass and stellar velocity dispersion, the M-sigma relation, or bulge stellar mass. Extrapolating these relations to JADESGSZ 140 predicts a black hole mass around 1 million solar masses, substantial but not dominant. Such a black hole would produce X-ray luminosities around 1042 erg/, if accreting at 10% Eddington, potentially detectable with future deep X-ray observations. Black hole growth through gas accretion follows well-understood physics. Gas falling toward the black hole forms an accretion disk, heating through viscous friction to millions of degrees. The disk radiates across the electromagnetic spectrum from X-rays to radio. For a 1 million solar mass black hole accreting at 1 solar mass per 10,000 years, the luminosity reaches 1044 erg/s, comparable to the galaxy's stellar luminosity. Such an AGN would dominate the spectrum, clearly inconsistent with observations. This implies JADESGSZ 140's black hole, if present, accretes much more slowly. Radiative feedback from AGN influences star formation through multiple channels. Intense UV and X-ray radiation ionizes surrounding gas, heating it and potentially suppressing cooling. Radio jets, when present, inflate cavities in the interstellar medium, pushing gas outward. In local galaxies, AGN feedback appears crucial for quenching star formation in massive ellipticals, preventing runaway cooling and excessive star formation. But at z=14, in galaxies just forming, AGN feedback may be less important. Supernova feedback dominates energy injection. The co-evolution of black holes and galaxies remains poorly understood, especially at early times. Local correlations suggest coordinated growth to more massive galaxies, host more massive black holes. But causality is unclear. Does the black hole regulate galaxy growth through feedback, or does galaxy mass simply determine how much gas reaches the center to feed the black hole? Observations at z equals 14 can test these scenarios by measuring whether correlations between black hole mass and galaxy properties exist at cosmic dawn or emerge later. Seed black hole masses constrain formation mechanisms. If JADESGSZ14-0's black hole formed from population 3 remnants starting with 100 solar masses at z equals 30, it would need to grow by a factor of 10,000 in 250 million years to reach 1 million solar masses. At the Eddington limit, black holes double their mass every 45 million years, allowing roughly 5 doublings, a factor of 32 growth. This falls short of 10,000, requiring either higher initial masses or super Eddington accretion. Direct collapse scenarios starting at 100,000 solar masses require only 3 doublings, easily achieved in available time. High redshift quasars provide comparison cases. Several quasars at Z is greater than 6 billion solar mass black holes formed within 900 million years after the Big Bang. These objects require continuous near-Eddington accretion from massive seeds, or super-Eddington phases, where accretion exceeds theoretical limits. JADESGSZ140 exists only 285 million years after the Big Bang, even earlier than these quasars. If it contains a million solar mass black hole, formation and growth timescales become even tighter. Gravitational wave observations offer future constraints. When black holes merge, they emit gravitational waves, detectable by space-based observatories, like LISA, Laser Interferometer Space Antenna, planned for the 2030. LISA will detect mergers of black holes with masses 10,000 to 1 million solar masses at redshifts up to z equals 20, revealing the population of seed black holes in the early universe. These observations will test whether black holes in galaxies like JADESGSZ140, formed via direct collapse, stellar remnants, or alternative pathways. The relationship between star formation and black hole growth may differ at cosmic dawn. In local galaxies, AGN activity and star formation appear linked starbursts, often accompany AGN episodes. But at Z equals 14, gas supplies are plentiful, and both processes can proceed independently. JADESGSZ140 may be in a phase where star formation dominates, with black hole growth delayed until later when stellar feedback clears the nuclear region, allowing gas to reach the center more easily. Future observations with the Nancy Grace Roman Space Telescope and the Extremely Large Telescope will search for faint AGN activity in high redshift galaxies through variability monitoring and high-resolution spectroscopy. Detecting variable X-ray or UV emission would confirm black hole accretion even when heavily obscured. These observations will determine whether galaxies like JADESGSZ140 harbour actively growing black holes, or whether black hole growth lags behind stellar mass assembly at the earliest times. The photometric redshift technique and its limitations. Measuring distances to galaxies billions of light years away requires precise techniques, and photometric redshifts have long served as astronomy's workhorse for this task. But the method carries inherent uncertainties that occasionally misidentify objects, placing them at incorrect distances. Understanding how photometric redshifts work and fail is crucial for interpreting discoveries like JADESGSZ140, especially given the explosion of high redshift candidates awaiting spectroscopic confirmation. Photometric redshifts estimate distance by measuring a galaxy's brightness through multiple filters spanning different wavelengths. Each filter captures light in a specific range, say 0.8 to 1 microns for one filter, 1 to 1.2 microns for another. By comparing brightness across filters, astronomers reconstruct the galaxy's spectral energy distribution, its brightness as a function of wavelength. This SED contains information about the galaxy's redshift, stellar population, dust content, and star formation history. The technique exploits spectral features that shift predictably with redshift. The most prominent is the Lyman break, a sharp drop in brightness at wavelengths shorter than 121.6 nanometers, caused by absorption from neutral hydrogen. In a galaxy at Z equals 10, the Lyman break shifts from 121.6 nanometers to 1.34 micrometers, moving through near-infrared filters. By identifying which filters show the break, photometric redshift algorithms estimate the galaxy's distance. Additional features like the Balmer break at 365 nanometers or emission lines provide further constraints. Template fitting forms the core of photometric redshift estimation. Astronomers create libraries of template spectra synthetic galaxy SEDs with various ages, metallicities, star formation histories, and dust contents. Each template is redshifted to different distances and compared to the observed photometry. The redshift producing the best match, quantified by chi-squared minimization, becomes the photometric redshift estimate. Uncertainties arise from template degeneracies. Multiple templates at different redshifts can produce similar photometry, especially with limited filters. For Z is greater than 10 galaxies, photometric redshifts become particularly challenging. The Lyman break shifts into the infrared, requiring observations with JWST's NIRCam. But dust extinction in lower redshift galaxies can mimic the Lyman break signature. A dusty galaxy at Z equals 2 with strong attenuation at blue wavelengths may appear similar to a pristine galaxy at Z equals 10. Distinguishing these requires additional constraints, emission line detections, morphological information, or deeper photometry. JADESGSZ140's photometric redshift, estimated at Z, is approximately equal to 14.2 from NIRCam imaging, carried typical uncertainties of plus or minus 0.5 to 1, significant enough that the galaxy could plausibly lie anywhere from Z equals 13 to Z equals 15. Only spectroscopic confirmation, measuring the precise wavelength of the Lyman alpha emission line, pinned the redshift to Z equals 14.32 plus or minus 0.02. This 100-fold improvement in precision eliminates ambiguity and confirms the galaxy's cosmic age at 285 million years. Catastrophic failures in photometric redshifts occur when entirely wrong templates match the data. A peculiar stellar population, unusual dust geometry, or strong emission lines can produce photometry inconsistent with standard templates. The algorithm, forced to choose something, may select a wildly incorrect redshift. Historical examples include several claimed Z is greater than 10 candidates from Hubble data that spectroscopy later revealed as Z is approximately equal to 2 dusty starbursts, embarrassing but valuable lessons in the method's limitations. Bayesian photometric redshifts improve upon simple template fitting by incorporating prior information. If we know from cosmological models that Z equals 15 galaxies should be rare, we can downweight solutions at that redshift, favoring more probable Z equals 2 alternatives, and less data strongly support high redshift. These priors prevent overestimating redshifts for marginal candidates. However, they also introduce circularity. We use theory to interpret observations meant to test theory. Balancing priors and data remains an active area of research. Multi-wavelength photometry increases accuracy. JWST's 8 NIRC filters spanning 0.6 to 5 microns provide robust SED sampling for Z is greater than 10 galaxies. Adding MIRI photometry at 7 to 28 micrometers further constrains dust emission and older stellar populations. The more filters available, the harder it becomes for incorrect templates to match all measurements simultaneously. With sufficient photometry, photometric redshift uncertainties shrink to deltas. 1 plus Z is approximately equal to 0.01, approaching spectroscopic precision. Emission lines complicate photometric redshifts in both beneficial and problematic ways. Strong lines, like O3 at 500.7 nanometers, boost flux in filters covering that wavelength, creating distinctive features in the SED. Algorithms accounting for emission lines can use this information to constrain redshift. If O3 falls in the 4.4 micron filter, the galaxy must be at Z is approximately equal to 8. But if emission lines aren't properly modelled, they produce bumps in the SED that confuse template fitting, potentially yielding incorrect redshifts. JADESGSZ140's photometric SED showed clear signs of a strong Lyman break, with detections in filters redwood of 1.8 microns and non-detections in bluer filters. This pattern strongly indicated Z is greater than 13, ruling out lower redshift dusty galaxies, but confirming Z equals 14.32 rather than Z equals 13 or Z equals 15.5 required spectroscopy. The distinction matters. A galaxy at Z equals 13 exists 275 million years after the Big Bang, while Z equals 15.5 corresponds to 235 million years. These 40 million years significantly affect inferred formation timescales and theoretical implications. Color-color diagrams provide visual representations of photometric redshift techniques. Plotting brightness in one filter versus another creates a two-dimensional space where galaxies of different redshifts occupy distinct regions. Lyman break galaxies, for example, appear very red in certain color combinations, separated from lower redshift interlopers. Multi-dimensional versions incorporating many filters improve separation further. Machine learning algorithms now use these multi-dimensional color spaces to classify galaxies and estimate redshifts with human-level or better accuracy. The future of photometric redshifts involves integration with spectroscopy. Rather than viewing them as competing techniques, astronomers use photometric surveys to identify candidates, prioritizing spectroscopic follow-up for the most interesting objects. JWST's JADE-S survey employed exactly this strategy. NIRCam imaging identified JADESGSZ140 as a high redshift candidate. Then near-spec spectroscopy confirmed and refined its redshift. This two-stage approach maximizes scientific return, using photometry's efficiency for wide-area surveys and spectroscopy's precision for detailed study. The Hubble tension and its implications for early galaxies. A crisis is brewing in cosmology, and JADESGSZ140 sits at its intersection. The Hubble tension, a discrepancy between different measurements of the universe's expansion rate has persisted for over a decade, despite increasingly precise data. Now, discoveries of unexpectedly bright and massive galaxies at cosmic dawn add fuel to the fire, suggesting either our cosmological models require revision or astrophysical processes in the early universe differed more dramatically than anticipated. The Hubble constant, denoted h0, quantifies the universe's expansion rate, how fast galaxies recede per unit distance. Two primary methods measure h0, and they disagree. Observations of the cosmic microwave background by the Planck satellite, combined with standard cosmological models, yield h0 equals 67.4 plus or minus 0.5 kmr divided by s divided by mpc. This measurement uses physics from 380,000 years after the Big Bang, inferring h0 through theoretical models of cosmic evolution. Local measurements using type Ia supernovae and Cepheid variables give h0 equals 73 plus or minus 1 km divided by s divided by mpc 5 sigma higher. This method builds the cosmic distance ladder, starting with parallax measurements to nearby stars, calibrating Cepheid period luminosity relations, using Cepheids to calibrate supernova brightness, and finally, measuring distances to high redshift supernovae. The systematic difference persists across multiple independent teams using different datasets, indicating genuine tension rather than random error. The discrepancy matters profoundly. If h0 truly equals 73, the universe is younger than Planck's value indicates about 12.8 billion years old instead of 13.8 billion. This billion-year difference affects ages of the oldest stars, timelines for galaxy formation, and cosmological models' internal consistency. For JADES-GSZ 14-0, observed at z equals 14.32, the age of the universe at observation changes from 285 million years, h0 equals 67.4, to 265 million years, h0 equals 73, a 20 million year difference affecting formation. Timescales. Beyond age, the Hubble tension might indicate new physics. Perhaps dark energy evolves with time rather than remaining constant. Maybe gravity behaves differently on cosmological scales than general relativity predicts. Or cosmological perturbations at recombination differed from standard model assumptions. Each possibility carries profound implications for fundamental physics, motivating intense investigation. Early galaxies, like JADES-GSZ 140, compound the problem because their properties depend on both cosmological parameters and astrophysical processes. If the universe is younger, higher h0, galaxies have less time to form, exacerbating tension between observed massive galaxies and theoretical predictions. Conversely, if h0 equals 67.4 is correct, galaxies have more time but apparently still formed faster than models predicted. Either way, something in our understanding requires revision. One resolution involves early dark energy, a component that contributes significantly to cosmic expansion at early times, but decays away by the present. This modification increases the expansion rate at recombination, shifting the sound horizon scale imprinted in the CMB. Recalibrating Planck data with early dark energy yields higher h0 values, potentially resolving the tension. But early dark energy introduces new parameters requiring fine-tuning, and independent CMB observations from ACT and SPT find little evidence for it. Modified gravity theories offer alternative solutions, If gravity weakens on cosmological scales or exhibits extra degrees of freedom, expansion history could differ from general relativity's predictions. Models like massive gravity or scalar tensor theories alter expansion rates without requiring dark energy modifications. But these theories must simultaneously match solar system tests, gravitational wave observations, galaxy dynamics, and large-scale structure, a challenging set of constraints that most proposals fail. Systematic errors in distance ladder measurements represent the most conservative explanation. Perhaps Cepheid calibrations suffer from metallicity-dependent biases. Maybe supernova standardization isn't perfect, introducing subtle evolutionary effects at high redshift. These possibilities remain under intense scrutiny. Recent independent measurements using surface brightness fluctuations, tip of the red giant branch stars, and gravitational lensing time delays all support H0 is approximately equal to 73, reducing likelihood of systematic error but not eliminating it. JADES GSZ 140's existence constrains some resolutions while remaining compatible with others. If the Hubble tension arises from early dark energy or modified gravity, structure formation proceeds differently at high redshift. Early dark energy accelerates expansion during matter radiation equality, suppressing small-scale structure formation. This reduces dark matter halo abundance at Z equals 14, making massive galaxies even rarer, worsening tension with observations. Modified gravity scenarios that enhance structure formation might help but require careful fine-tuning to match all data. The sigma-8 tension, a related discrepancy in measurements of matter clustering amplitude, intersects with early galaxy abundances. Planck CMB data indicate sigma-8 equals 0.81 plus or minus 0.01, while weak gravitational lensing surveys yield sigma-8 equals 0.77 plus or minus 0.02. Lower sigma-8 means weaker clustering, fewer massive halos at high redshift, and fewer bright galaxies. If sigma-8 truly equals 0.77, JADESGSZ14-0's existence becomes even more puzzling, requiring either extreme astrophysical efficiency or non-standard cosmology. Neutrino masses provide another potential connection. Massive neutrinos suppress structure formation on small scales because their thermal velocities allow them to stream out of overdense regions. Measurements of sigma-8 constrain the sum of neutrino masses to below 0.12 electron volts. If neutrinos are heavier, structure forms more slowly, reducing galaxy abundances at high redshift. But particle physics favors neutrino masses around 0.06 electron volts based on oscillation experiments, leaving little room for cosmologically significant effects. Reionization history links to early galaxy populations and cosmological parameters. More galaxies at Z is greater than 10 means more ionizing photons, accelerating reionization. CMB polarization measurements constrain the ionization history through its impact on electron scattering. If reionization completes by Z equals 6, as currently favored, the implied ionizing photon budget requires either numerous faint galaxies below detection limits or higher escape fractions than measured locally. JADESGSZ140 contributes to this budget, but doesn't dominate, implying abundant, fainter sources